their frame. So therefore, my temporal resolution is going to decrease. Okay? My frame rates are going to decrease. My T-frame is going to be higher because now it's going to take longer to create this one single image.
It still has nothing to do with the image.
Yeah, it's going to change the image because, this changes the quality because now I have more information. Now I'm sending out enough pulses to get a lot more information in between those gaps. So now I'm getting more accurate information. And now my machine is not making up as much information as it does, as it normally does. Okay. So line density and frame rate. I can just put this right here, guys. I'm just gonna put this in comments right here. Focal zones. Because there's 3 of them, right? Focal zones. What else we got? Sector width. And line density. They all have an inverse relationship with frame rate. My frame rate is going to go down if I happen to increase the number of scan lines needed to create an image. Some ultrasound systems allow you to change the spacing, whereas other spacing is automatically done and it can't be manipulated. IU22, you can manipulate the line density on there. You can manipulate the line density on IU22. Okay? What is the main advantage of high line density, guys? Improved spatial. Spatial is also known as detail resolution. That's why I was saying I'm going to get to it, Myron. Also known as detail resolution. Because now I'm acquiring more information now. I'm missing less information. You know, it's kind of like with a CAT scan. With a CAT scan, like if I'm scanning, right, Pat? If I'm scanning in my table, and let's say I'm taking an image every 5 centimeters, you know, I'm probably going to be done with that scan a lot faster than if I'm scanning the image every 1 centimeter, right? If I'm then I'm going to be done a lot faster if I'm scanning at 5 centimeters compared to 1. But if I'm scanning at one centimeter per image, then I'm getting a lot thinner slices, meaning I'm getting a lot more accurate information, right? Instead of me, I'm cross-sectioning the body at the heart. Now I'm cross-sectioning the body at the liver. Now I'm doing it at the umbilicus. Now I'm doing it at the waist. You know, I'm getting more slices now. I'm getting more accurate information now because I'm sending out more scan lines. So that's going to improve my image detail. I hope that was a good analogy.
That was good.
So the smaller the space, that it makes a better lateral resolution?
No, the better spatial or detail resolution.
Because you're able to see images side by side.
You're able to have more accurate information because now I'm having basically I'm getting all of the information in that space in between the lines as well. And I'm not having big gaps in between. Because remember, the beam, as the scan lines go out, they're going to get further and further apart, right? So if I have another scan line right in between here, now I'm not missing all of this information right here. The ultrasound, that's what happened. The ultrasound system makes up, if I have these 2 scan lines right here, this is line density, this space between my scan lines, between my arms. So now I'm missing all of this information right here because I have, boom, I sent out that scan line, boom, I sent out this scan line. But the ultrasound system is going to make up this information based on the information it got here and the information it got here. But now if I send a scan out line out right here, and I send a scan out line out right here, and I send another one out here, now it doesn't have to make up as much information because now my line density is smaller now. You got me?
Can you go back 1 slide? On the lower frame rate, say then line density is larger, but the distance between the 2 sound beams it look like smaller than the other one.
My line density is high. I have a high line density. Yeah, because I'm having more lines per image. My line density is higher. the amount, remember density, the amount of lines in this one image is a lot more than this image.
Because they say line density is the spacing between two sound beam, right?
Mm-hmm.
This is that equal n as well?
It's not a number. It's not like a measurement. It's not like I'm not measuring the distance between
Okay.
that. It's not like, oh, that's 2 centimeters. Right? It's just saying that that's what it is. The space in between each of these is gonna be the line density. So it's less space in these scan lines, meaning I'm gonna have a higher line density compared
Okay.
to this space right here.
I see.
I have more space here, but I have a lower line density.
Got it.
Okay. So again, line density, it affects spatial resolution. If I have a high line density, then I'm gonna have better detail resolution. Again, just like slice thickness and the elevational resolution, detail and spatial resolution mean the same thing, they're synonymous terms. Okay? A high line density is bad for temporal resolution, and the gaps between the lines are small. Okay? If I have more scan lines, as simple as that. I have more scan lines, it's taking longer to create that one image.
Right. Frame rate decrease.
Frame rate is going to decrease. T-frame is going to increase, because now it's taking a longer time for that one image. Okay? Remember, there's a trade-off between temporal and spatial resolution when deciding to use high line density. Okay? Start right there. So again, this, and the only reason I'm sharing these pictures is because we have Philips machines over here. We use a GE Logic. At my other job, I wanted to show you that not only do we have it on our RU22s, they're on all machines. But it's a GE Logic, an old one by the way, and our line density is set to 2. I think it has between 1 through 4 on the line density scale. Okay, but that's where you change the line density at right there. Okay. All right. So this is our summary of the number of pulses per image. This is our original image right here, right guys? We have, pretty heavy line density, but now we have a reduced amount of depth. So our temporal resolution is gonna be better, right? Because our depth is shorter.
Mm-hmm.
Our temporal resolution is gonna be better because we're gonna have higher frame rates because we're able to acquire more images now because we have a shallower depth. Okay? Also, we have on the line density, we went from having a real heavy line density or a lot less space between the scan lines to a lot more space between the scan lines. So now instead of like, I don't know how many this is, 20 right here, scan lines, instead of that we have 3, 6, 8 lines to make this one image. We're gonna be able to acquire these images a lot faster. But we're gonna lose image detail. Right? Because now my machine has to make up this information in between this space now. It has to make up that information. I'm really saying it makes it it's an algorithm it takes these 2 scan lines and kind of makes the information between those 2. Okay. And also, we're gonna have reduced field of view now with the sector width. The sector width now, instead of the original image being a real wide image, or a reduced field of view, that's not going to affect the quality of the image. That's only going to affect the speed at which that image is acquired. Okay.
Is speed important?
It depends. It depends. All of those have. I'm coming to that's why I said this. It has increased frame rate. All of those are going to have increased frame rate from the original image. My frame rates are going to increase because I use less depth.
Shallow picture.
A shallow image. My frame is going to increase because I have a lower line density. My frame rates are going to increase because now I have a smaller field of view.
Mm-hmm.
Okay. Remember, number of focal points, it affects lateral resolution. Okay. When we're talking about line density, we're talking about spatial and detail resolution. Okay. We're talking about sector width. We're not talking about the quality of the image. We're only talking about the speed in which it's acquired, the time. Okay. So, do our resolution review. Guys, axial resolution, that's the resolution of identifying 2 structures that are closer together, that are front to back. are parallel to the sound beam, right? Two structures that are parallel to the sound beam's main axis. Okay? Lateral resolution has the ability to identify two structures that are side by side, okay, or perpendicular to the sound beam's main axis. Okay? We also have slice thickness and elevational resolution. Right there, guys. That's the ability to discern between two structures that are also perpendicular to the sound beam, but above and below the imaging planes. Okay. Next up, we just learned about these today. Temporal resolution. Okay? That's the ability to predict precisely position moving structures from instance to instant, like the heart. Okay? And we have spatial and detail resolution, which we learned about today as well. And that is related to overall detail of image. Image quality is going to be better if we have a higher spatial or detail resolution. Okay. So these are all our resolutions we learned up to this point. Okay? I'm almost done, guys. Because I can't believe I got through the whole lecture in one
That's
class.
a lot of information.
It's really not. If you think about it in segments, it's not a lot of information. I'm talking a lot, but it's really not a lot. Okay. How are temporal resolution and image quality related? So we have to understand: do we want an excellent picture, or do you want an excellent movie? Okay. If I'm imaging the heart, for example, then I really want a really great movie. I want to be able to see those valves in the heart moving, at exactly the time they're moving.
So that's when speed is important.
That's when speed is important. When I'm trying to look at a structure that's moving. If I was trying to time the movement of the diaphragm, that's when it would be important.